In this video, we'll cover shifting Equilibria Le Chatelier's principle. Take a look at this seesaw. On the left-hand side, you will see A plus B. Those are the two reactants forming into C plus D. Now, also notice the symbol in between the reactant and the product, and that's the two double-headed arrows, which indicates that it's going into the forward and the reverse reaction. In fact, it's at equilibrium. Because it's at equilibrium, there's a balance of the reactant and the product. It doesn't necessarily mean there's more or same amount of product and same amount of reactant, but it's showing that it is at equilibrium. The rate of going forward and the reverse reaction is exactly the same. If there is a change where there is more now of A and B, the reactant has been allowed to be put into the system, this equilibrium system. It's no longer at equilibrium. But what it's going to try to do is it's going to try to reestablish the equilibrium by making the reaction go forward in the forward direction so that it will level out the teeter-totter or seesaw. And it goes in the other direction as well. If it were to go in such a way that there's more of the product or whatever case, making the product heavier or more, then it's going to drive the reaction in the reverse direction so that the product will reform the reactant and forming a balance. This type of reaction, we can say that if it goes out of equilibrium, then reaction will always reestablish the equilibrium, either going in the forward or the reverse direction. And in simple, or I shouldn't say simple, but I should say more in a fancier term, this is the Le Chatelier's principle. And it just states that, hey, if there is a stress in the equilibrium, meaning if it went off the equilibrium, the reaction will, whatever it does, it will reestablish that equilibrium. It'll do what it takes, either by making more of the product or making more of the reactant. So we're going to look at some few scenarios in which the reactant and product are going to start being shifted. So here's a reaction where hydrogen and iodine forms into hydrogen iodide gas. And it's at equilibrium at 50.0, that's equilibrium constant, and then at 400 degrees Celsius. But what happens is that reactant and the reactant H2 and the I2 concentration starts to increase. There is more of this reactant being added. So say you have a lot more of the reactant. So what it's going to start to do is it's going to start to change the equilibrium, meaning it's no longer even at the equilibrium. It's going to try to adjust it so that equilibrium is reestablished. So if the reactant was added, then what that means is the QC, or the reaction quotient, is bigger and the reaction will go in the forward direction. It's going to go into the forward direction. I'm going to go ahead and write the QC equation, which is here the product to the second power, and then H2 and I2. So what it's essentially saying is, hey, I am adding a lot of the reactant. So I am adding a lot of this. So the denominator is increasing. If the denominator increases, that means the QC will start to fall down. If the QC starts to fall down, it'll be under the KC. It'll be under maybe like 30, 20, who knows. And then so therefore it's going to allow forward reaction to take place. Another case scenario is you're going to have not reactant including, but rather product is being excluded, meaning you're removing the product. So if you're removing the product, right? If you start to remove the product, then this teeter-totter will also go out of shift the equilibrium. And in that case, you're saying, hey, we're taking this portion of the product and we're going to decrease it. Well, if you decrease the numerator, then that's going to decrease the QC, making this QC less than the KC. Therefore, this will make equilibrium shift to the right. So it's two scenarios you see here. You're adding either more of the reactant, okay, or you're removing the product. Those are the two potential scenarios in which the equilibrium will shift forward or the reaction will go in a forward direction. Here's another scenario. The other scenario is in which the product, there is more of it. So for example, more product has been added. So here, more product has been added. Or we can say also where reactant has been removed. Reactant has been removed. In this scenario, what's going on is that the QC will be increasing. It will go higher than the equilibrium constant KC. I mean, this is the numerator will be increasing, so therefore QC increases, or where this reacting is diminishing, and you know that the denominator decreasing will make the QC increase. That will cause a reaction to go into the reverse direction. Simply said, all of these scenarios are based on concentration. So if there's a change in concentration, what's going to happen? The equilibrium will start to reestablish to make the concentration ratio to be the same to reestablish Kc. Here is another scenario. Another scenario would be changing the temperature of the equilibrium, which shifts the equilibrium either to the left or to the right, forward or reverse. So in this system over here, you have dinitrogen tetroxide forming into nitric dioxide. That 2 should be a subscript, so I'm going to go ahead and erase that, and that should be a little 2 there. Okay. Now, also notice on the very right, it says delta H is equal to the 57.20. What does that mean? It means that this reaction is an endothermic reaction. An endothermic reaction means that there is an input of energy or input of heat into the system, into the reactant side. So you'll see right here, I have added heat. If it was a negative value, then if it was a negative delta H, it would have been on the product side. So in this scenario, when we have added the heat in order for the reaction to occur, and there is a change in temperature, like say you increase the temperature, then that's going to cause the reaction to go to the right. So you add heat, so you raise the temperature, or adding heat of the system will shift to the right or going into the forward direction. If you were to remove the heat, if you were to remove this heat, then it's going into reverse direction. Treat the heat as if it's a concentration unit, right? As if you add more of this, and it's going to go into forward direction, just like if you were to add more of the N2O4. And if you were to remove this, or if you were to remove this, it's same thing. It's going into the reverse direction. Well, what if it was a negative delta H? So say, for example, this is just on top of my head. It's not saying that it is reaction A plus B going into reaction C, and that delta H is negative 41 kilojoules. Well, this tells me the heat should be on the product side, and so it's going to go in reverse. So if you raise the temperature here, then it's going to go into reverse direction. If you lower the temperature, then it's going to go into the right direction. So let's go ahead and do a learning check based on what we have learned so far. Suggest 4 ways in which the concentration of hydrazine could be increased in an equilibrium described by the following equation. So here are some clues that I can give to you based on this equation. You see that delta H, the enthalpy, shows 95 kilojoules. What does that mean? It's an endothermic reaction, meaning that it had needed to input heat before the reaction occurred. So I'm going to put heat on the reactant side, plus heat. So hopefully you can come up with 4 ways. Come back and check this video. So first way in order to do this is to increase heat. By increase heat, you will increase the production of hydrazine, N2H4. If I were to add more of the nitrogen gas, that will also drive the reaction forward. Lastly, adding more of the hydrogen will drive the reaction forward. Or not lastly, second to last. Now, finally, lastly, if I were to remove N2H4, that will cause the reaction to go forward because you're removing this, you're taking out this hydrazine, and that's causing the balance to teeter-totter to go like this. And then so we wanted to reestablish, so that will drive the reaction forward if I remove this. In the last scenario, and it doesn't really apply to the Le Chatelier's principle, but I think it's good to know in regards to catalyst. The catalyst will cause whether the reaction to go into the forward or reverse reaction in such way that it lowers the activation energy. Say you have a reaction going, and that causes a reaction to form a product. So here is reactant side, and here is product side. And in order for that reaction to occur, it needs to go through this hump or this transition state. In order to go through that state, it needs input of a lot of energy to form a product. But what the catalyst does is that it could be a metal, it could be an enzyme. Something will lower that transition state. So it doesn't have to spend much energy in order for it to form a product. So it will lower the activation of energy, and it will increase the rate of going into the forward and the reverse reaction. So it'll make things go faster. But it doesn't necessarily change the equilibrium constant, nor will it change whether it's going to go into the forward direction or the reverse direction. It only just plays around with lowering that energy, but it's not going to drive either in the forward or the reverse direction. So let's do a learning check based on what we have learned so far. Methanol, here's methanol, can be prepared from carbon monoxide and hydrogen at high temperature and pressure in the presence of a suitable catalyst. So it shows you a balanced equation. Now we will go through all these series of questions and answers throughout the rest of the video. A, write the expression for the equilibrium constant. So it wants you to write Kc. So let's go ahead and write Kc is equal to the product, which is methanol, to the first power. And then we have carbon dioxide to the first power, and we have hydrogen to the second power since the coefficient is 2. Then it asks what happens to the direction if more hydrogen is added at equilibrium. So if you're adding more of the reactant, okay, we're going to cause a reaction shift to the right or forward. So there'll be a shift in the forward direction. What happens if the reaction where carbon monoxide is removed? Oh, why is there a dioxide? This should be removed. Should be O. If CO is removed, well, if you're removing this, okay, if you're removing this, you're going to want to have all of these guys to go into the reverse direction to replace that. So it's going to go into the reverse, shift, reverse direction. Lastly, it says what will happen to the concentration if getting all kinds of mistake here, if H2 and CO and methanol at equilibrium, if methanol is added, okay? So what's going to happen to each of the concentration if methanol is added? So if more and more methanol is added, it means that it's going to cause a reaction equilibrium to go to the left. So if it goes to the left, the concentration of H2 will increase, the concentration of carbon monoxide will increase, and the concentration of HCO methanol will decrease because you're going to be driving that reaction in the reverse direction. Now, second to last, what will happen to the direction of the reaction if the temperature of the equilibrium system is increased? So notice that this is an enthalpy, negative enthalpy, and so that means that it's on the heat is on the product side. So if I were to increase the heat, so I'm increasing the product side, it's going to go into the reactant, so it'll go in the reverse direction. Shift, reverse direction. What will happen to the equilibrium if more catalyst has been added? So we just talked about that, and then the catalyst, there's nothing, no change.